We're going to review some right triangle trigonometry so that you have this skill, this knowledge in place as we move towards vectors and decomposing and resolving vectors. The first thing we need to attend to is making sure that we're familiar with angles. All right triangles have 3 angles, and we need to know about angles. I'm going to remind you that one revolution in one circle is 360 degrees, which is 2 pi radians. We may be given angles in radians. We may need to express them, so familiarity with radians is going to be a benefit for you. And you can see that angles are measured counterclockwise from the positive x-axis. So if I think about a regular coordinate system and lay that on there, if this be the y direction and this will be the positive x direction, we can see that the 0 angle is at this positive x-axis. All of the rest of the angles are measured positive in a counterclockwise direction, okay? If we measure anything in the clockwise direction, like this, we would say that it would be a negative angle. So for instance, negative 60 degrees, if I go negative 60 degrees, I'm going to note that that is a positive 300 degrees, okay? Let's practice angle conversion. We're going to convert from degrees to radians and radians to degrees. I'm going to remind you that the conversion factor, and this is very similar to unit conversion, the conversion factor is that there's 360 degrees and 2 pi radians, and that is an easy thing to remember. So when I think about converting 72 degrees, I'm going to use the ladder method like I normally would. I want to cancel out degrees, which means I would put 360 degrees on the bottom, which means that I put 2 pi radians in the top. Notice that the degrees cancel out and I'm left with just radians, which is what I wanted to do. And when you do this, you can plug it through your calculator. You would get 1.3 radians. You divide by 360 degrees, that's a pretty big number. We can do the same thing and go backwards, 2.8 radians. I'm going to draw a ladder so I can convert. I have radians in the numerator, so I'll put radians in the denominator. 2 pi radians is 360 degrees. Notice that the radians cancel like I expect them to, and I get 160 degrees out of that. So now you can easily convert between degrees and radians degrees with this one simple conversion factor. More particularly at the special properties of right triangles. And a right triangle has one 90-degree angle, and you can note that in the triangle that I've drawn here. We designate the right triangle with a little box down here designating that this is a perpendicular relationship between these 2 lines. The other 2 angles in here, these 2, must add up to 90 then, because if this is 90 and they all add up to 180, there's 90 left. So these 2 add up to 90, and we call that complementary. In a right triangle, C is labeled the hypotenuse. Notice that it is across from the right angle. Right? When I think about angles, that is often something that we do, is we will talk about the leg that is across from an angle. It is the longest side of a right triangle, and if you remember the Pythagorean theorem, a squared plus b squared equals c squared. So it's a very special relationship for this triangle that a squared plus b squared equals c squared, and c is the longest leg, the hypotenuse. It turns out that the ratios of the sides of a right triangle are related to functions of the angles. Okay, so this is very basic right triangle trigonometry. For any angle theta in a right triangle, and I arbitrarily labeled this angle down here theta, we can define an adjacent leg, and notice that I've labeled that as well. The adjacent leg and the hypotenuse form the angle. That's why we call it the adjacent leg, because it's right there next to the angle. The opposite leg is the leg that does not form the angle. It's across the triangle from it. So when you're looking at right triangle trigonometry and having a hard time with opposite and adjacent, the opposite is across, the adjacent is right next to it. And so this brings up these ratios. The ratios of the sides of these triangles are related to the angle. And we call these function of the angles, the sine of the angle, the cosine of the angle, and the tangent of the angle. And these are the abbreviations for sine, cosine, and tangent. So the sine of the angle is the ratio of the opposite leg over the hypotenuse. So if I knew the measure of the opposite leg and I knew the measure of the hypotenuse, I would just take that ratio. And that's what the sine is. The cosine is the adjacent over the hypotenuse, so I take the length of the adjacent leg over the hypotenuse, and the tangent is the opposite over the adjacent. So I get these three relationships. This is reduced down to the mnemonics SOHCAHTOA so that you can remember which of the legs of the triangle go together for which trig function. Let's do a practice problem with just this basic trig functions. For the triangle shown, the green one, theta equals 42 degrees, and you can label this in your picture, 42 degrees, so that's a known value. C equals 85. We're not given any units. We don't necessarily need to know units. We just know it's 85 units, whatever units. Solve for A and B. Oh, very interesting. So we're given the angle, and we have the hypotenuse. Notice that C is the hypotenuse. So I'm going to write this over here. H equals the hypotenuse, which is C, which is 85. Okay. So if I want to find A and B, A is going to be the opposite leg. Notice it's across from theta in the triangle. B is the adjacent leg. It's right next to the angle in the triangle that we know. So I have hypotenuse, opposite, and adjacent. I know the hypotenuse. So when I think about SOHCAHTOA, I'm going to note that SO and CA have H in it, right? The hypotenuse. Tangent has opposite and adjacent, and we don't know either of those. So if I know sine of 42 equals the opposite over the hypotenuse, so when I think about this, the opposite leg is A, and the hypotenuse is 85. I'm going to note that in this equation, the only unknown is A. I can find this opposite leg, this leg we've called A, and I can calculate it. I'm going to multiply by 85 on both sides. You can do a little bit of algebra here, sine 42 degrees. And when I plug this into the calculator, you will get A is 57. You round it off, 57. Okay. So that's easy enough. I'm going to do the same thing with cosine. Cosine 42 is the adjacent over the hypotenuse. The adjacent leg is B. The hypotenuse we know is 85. I'm going to solve B equals 85 times cosine of 42 degrees. And when you plug this into your calculator, you just plug it into your calculator. Make sure that your calculator is in degrees. You will get 63. Done. Let's work on the blue triangle. For the triangle shown, theta equals 29 degrees. I'm going to put that in here, 29 degrees. B equals 85. Oh, interesting. So we're given the opposite leg. Notice when I'm looking at this equation, I'm going to note that I'm given the 29 degrees and B is the opposite leg. Notice it's different than over here, the previous problem where I had B be the adjacent leg. So always watch out which angle you're given, and then assign opposite and adjacent after that. So the adjacent leg is A. A and C are legs used to make this angle theta. Okay, so solve for A and C. So I'm going to notice that I have the opposite. Known value is the opposite. And so when I think about SOHCAHTOA, the sine has opposite in it and the tangent has opposite in it. So the opposite is the known value, and I also know the angle, so I can find the hypotenuse from one and the adjacent leg from the other. So let me write this out. Sine 29 degrees is opposite over hypotenuse, so I'm going to get B over C, which is 85 over C. We're going to do a little bit of algebra here. You can do this on your own. You get 85 over sine 29 degrees, and you can plug this into your calculator. We're going to get C be a large number. It should be larger than B, right? It should be the largest leg of the entire triangle, and I get 175. We'll do tangent here. Tangent 29 degrees equals opposite over adjacent, which is B over A. I know B is 85, but I don't know A. I can solve for A though, do a little bit of algebra on this equation. I get 85 over tan 29 degrees. And when you plug this into your calculator, you get A is 153 units. Those are basic applications of SOHCAHTOA with right triangles, no context. Let's look at inverse trig functions. As we know, the trig functions, sine, cosine, and tangent, those are all in SOHCAHTOA. We will want to be able to go backwards in some way, right? If we know the legs of a triangle, can we figure out the angles in the triangle? And the answer is yes. And how we do that is with the inverse trig functions. Notice if I know the legs of a triangle, opposite, hypotenuse, adjacent, opposite, adjacent, I can use the corresponding inverse trig functions in order to find the angle. And they kind of undo this ratio, right? A ratio of opposite over hypotenuse has to correspond to a certain angle, has to. And so we can use this in our calculator in order to calculate angles. I have an example for the triangle shown, this green one here. A equals 5 and C equals 19. So let me put this in there. 5 and 19, I know those two. Let's see, if this is theta, then this means this is the adjacent leg and this is the hypotenuse. So when I look at this, I have adjacent and hypotenuse. This corresponds to CA, right? So CA, TOA, adjacent and hypotenuse, which means that I need the cosine of theta equals 5 over 19. Okay. So how do we isolate theta in this equation, which is why we use the inverse trig function. It's sort of undoing the function. So what I would do is the cos negative 1 of cosine theta equals the inverse cosine of 5 over 19. And notice what operation I did on one side of the equation I did on the other side of the equation. This is very typical. For instance, if I had the square root of 4 equals x. If I square both sides, right, I have to square both sides, and that would, when I do an operation, I do it on both sides, okay? So we're going to note that cosine inverse times cosine, or just the operation of cosine inverse on cosine, kind of cancel each other out. They undo each other, which is what, when you take the square of a square root is what happens. They undo each other. So I'm going to get theta equals the inverse cosine of 5 over 19, and when you plug this through your calculator, you will get about 75 degrees. Okay, pretty straightforward. And that's how to use an inverse trig function. We will be using this more as we move into more material. I just have an example here, calculate x. I'm not sure, I don't think that there's inverse trig functions here, but we can solve it. Calculate x in the figure. X is right here. And what I'm going to note here, I'm just going to point this out for us, that there are two right triangles. There's the larger one here, right? And I'm going to note for this larger one that it has a really long side, right? I'll call this side Z. They call that one X. I'm going to call this Z. And when I look at side Z has two components. It has this component X, right? Goes into it. And it also has this component Y. And notice that Y is on a second right triangle right here, okay? And I'm isolating down to right triangles because I can use trig on them. And so if I wanted to solve for x, wanted to solve for x, I would take z and subtract y. And that's going to be my general strategy for this problem is I'm going to find z from right triangle trigonometry. I'm going to find y from right triangle trigonometry. When I get those two values, I am going to simply subtract them, and that will give me this x value. Okay. So we are given this angle 26 degrees, and we are given the side opposite the 26 degrees. I'm just going to put an opposite here. Also, we're given the 70-degree angle, and it is opposite. Okay. What we're asked to find, or what we're planning to find, are the adjacent legs. Notice these are both adjacent legs. Z is the adjacent leg, and Y is the adjacent leg. So opposite and adjacent suggests tangent, right? So toa. T is opposite tangent. Theta equals the opposite over the adjacent. So it seems like we're going to have to do this twice. We're going to have to do it once with the larger triangle with the 26-degree angle, and we're going to have to do it again with the smaller triangle with the 70-degree angle. So let's do this. Tan 26 degrees equals 119 over z. And also tan 70 degrees equals 119 over y. I can solve both of these equations for z and y. Z equals 119 over tan 26 degrees. Y equals 119 over tan 70 degrees. So then when I go to plug these in, I'm just going to take these values and plug them in over here. I get 119 over tan 26 minus 119 over tan 70. You can calculate these separately. You could also go, notice that I have 119 in both terms. So you could simplify this a little bit more and factor out 119. And when I calculate this, I'll put this over here, I get x equals 200.67, which you could round to 201. Is what x is. So we used a couple of trig functions. This is an applied problem, a couple of more steps in problem solving to get to our answer. And the trick here was to note that we had two different right triangles. Here's an example of right triangle trigonometry that involves velocity. Velocity is a vector, and it has two components in an x and y coordinate system. When an object in projectile motion hits the ground, the velocity is composed of a horizontal component and a vertical component. So when I think of something hitting the ground, it's saying, here's the ground. It's hitting the ground with a horizontal component and a vertical component to the velocity. And I will label these Vx and Vy like they have in the problem. Okay. Those two add like vectors together and result in this sort of resultant velocity, this overall net total velocity, V net. And what I'm going to note is V net is a vector, and you add Vx as a vector and with Vy as a vector. But what we're going to note is this is a right triangle, right? The horizontal component and the vertical component are to right degrees with a right angle with one another. And I just created a right triangle with these three vectors, right? I can't just add the two. I can't say Vx plus Vy, right? 8 plus 19. I can't say that's the net one. Notice in this situation, I have a right triangle, and so a squared plus b squared equals c squared is going to be the right way for me to go in order to calculate the net velocity. And the way we will do that is V net. All right. We want the magnitude of it. And I'm going to model this from c squared equals a squared plus b squared. So V net has to be Vx squared plus Vy squared and square rooted with a little bit of algebra. I can do that. Vx squared, Vx is 8, so I can take 8 squared, add on Vy, which is 19 squared, and we're going to square root both of those. And I get the magnitude of V net is 20.6 meters per second. Very straightforward. They give me two legs of a right triangle. I can easily find the third one. The idea here is that we have a horizontal component and a vertical component in our total velocity vector, our net velocity. Okay, so it says find the magnitude and direction. Okay, direction. So this is where the right triangle trigonometry comes in, the direction of this velocity vector. Notice that I have it drawn at an angle with respect to the horizontal, right? And when I think about this angle, I know two sides of the triangle. I know there's 8 on one side and there's 19 on the other. And when I look at this, I have the opposite leg, right? 19 is the opposite, 8 is the adjacent. So that suggests to me tangent, TOA, right? Tangent from SOHCAHTOA. The tangent of theta has to equal the opposite over the adjacent. So I can plug this stuff in. Let's see. The tangent of theta is the opposite, 19 over 8. Okay. I'm going to do the inverse tangent function on both sides, which will allow me to bring out just the theta, right? I'm undoing these two functions and theta remains here, and I get this to be the inverse tan of 19 over 8. When you plug this into your calculator, you will get a value of 67.2 degrees, okay? Staying consistent with measuring from the horizontal, you may say 67.2 degrees below the horizontal. I'm not going to, you could do a negative 67.2, but that's assuming that the horizontal is positive. A lot of times in this situation, they will just say below the horizontal, and notice that's because we're measuring below the horizontal. If it was pointing upward, that would be above the horizontal. So that's how you would find the magnitude and the direction of a net velocity vector. An example for trig functions has to do with total acceleration. The total acceleration vector may be composed of multiple components. And when we're moving in circular motion, so I can make maybe a circular curve here with a radius r, right? Here's a radius r, okay. An automobile in a circular curve experiences a tangential acceleration of 2.3 meters per second. So tangential means tangent to the circle. If I choose a point, any point along here, I'll just choose right here just for convenience. It's moving, let's say it's moving in this direction. The velocity is in that direction. It's telling me that it has a tangential deceleration. So that means that the tangential acceleration points away from the velocity vector, right? It's slowing down in that direction. So there's the tangential acceleration. And also, let's draw another one in here. I will draw the radial acceleration. So radial means along the radius. So there is an acceleration that points towards the center of the circle, and that is a radial acceleration. So we have a tangential one and a radial one. And notice that when I do this, they are perpendicular to one another, these two. And when I add them together, if I take a tangential and I add on, and you can use the polygon method, let's see, AR, right? Because I have it drawn tail to tail here, but if I add them together, head to tail, I can take a tangential, add on AR, and I get a resultant acceleration, which we were going to call a net. And these are all vector quantities. We're going to note that we do have the situation with a right triangle. If I want to find the magnitude of a net, not too hard. I do the square root of a radial squared plus a tangential squared. And I would easily find the, let's see, the value. I can easily find the value of the net acceleration by plugging in what I know here. The radial is 4.7 I can square that. The tangential is 2.3. I can square that. It doesn't matter what order I add these, right? I'm adding them and squaring them and adding them. I'll get the same thing. So pretty quickly, I can get the magnitude of the net acceleration, which is 5.2 meters per second squared. I'm going to keep the same units. They're both in the same units. There's the units. They also tell me to find the angle. So determine the magnitude and the angle of total acceleration. Makes with respect to its forward motion. So when I look at this problem, I'll put a different color in here. The net acceleration, notice that the velocity is in this direction and the net acceleration is there. So they want me to find this angle. What is this angle? Theta, right? With respect to the going velocity. And I'm going to note that that is 90 plus this angle, whatever that angle is, which is the same as this angle. I'm going to call this angle, what am I going to call it? Gamma. I'll call it gamma. Okay. So if I want to find theta, it will equal 90 plus gamma, whatever gamma is. So let's use a trig function and find gamma. In our equation, in our triangle, we're given the opposite leg. Notice this is the opposite, and we're given the adjacent. So we're going to use tangent. I'm going to note tan alpha equals a tangential over a radial, the values of those two accelerations. Which will tell me that my angle gamma is the inverse tangent of the tangential, which is 2.3, over the radial, which is 4.7, and I can close that up and calculate it. When you run this through your calculator, you get 26.1 degrees. If I want to find theta, which is what they're asking me for and what I've labeled in my diagram here is theta, I'm going to take 90 degrees plus 26.1 degrees, and I am going to get 116.1 degrees. That's the trick for finding the magnitude, Pythagorean theorem, and the direction. You can use trig functions, in this case tangent, in order to find angles and add them up. I wanted to review a few simple trig identities that you may see come up. Sine over cosine equals tangent. This is a frequent strategy. If you don't know the angle, if you take the ratio of sine over cosine, you can get tangent, and this often happens in systems of equations. The proof here is you can use a definition of the function. Sine is the opposite over the hypotenuse, and cosine is the adjacent over the hypotenuse. The hypotenuse cancels, and you get adjacent over opposite over adjacent, which is tangent. Very slick proof here. The other one is the Pythagorean identity, which sine squared plus cosine squared equals 1. And if you start with the Pythagorean theorem and divide by the hypotenuse, all of the terms you divide by the hypotenuse squared, notice that you get a over c squared, b squared over c squared, and c squared over c squared. And I can plug in what I know about a over c and b over c. Those are both sine and cosine, and those terms are squared. So I get this nice relationship. These may come up as we move forward into the material, and so you're familiar and ready to use them. Other general triangle trig properties that you can keep in mind is the law of sines. Notice this is the sine of the angle over the opposite leg, and that's why I was mentioning earlier. When we label angles, we keep track of the leg opposite from them, and you can see this is used here with the law of sines, the sine of the angle. All of these ratios are equal to one another, and I'm going to note if you put it in the other direction, a over sine alpha equals b over sine beta. You could use it that way as well, but typically the sine is on top. And all those ratios are equal to one another. The last thing here to remind you is the law of cosines. It looks familiar, right? If I didn't have this last term, it would look like Pythagorean theorem. And this is a general triangle that doesn't have to be a right angle. If you have any sort of angle in there, if you're trying to find C, and notice that C is across from gamma in the triangle that I have as the example here. All right. So when we try to find C here, the angle that would go into theta will be actually gamma. That will be the angle that goes in here.